Hey everybody, welcome back. Our next order of business is really to do some work with math tools. Science has a lot of math in it. I used to teach math for many years, and one of the things I kind of joke with my colleagues is that the math that I was teaching, or the math that all of these teachers were teaching, was really just a tool, right? And I know that we study for math for like math's sake, but it often doesn't make a lot of sense. In fact, in math classes, when I taught math, one of the questions that I got asked the most from my students was, Mr. Wilson or Mr. Barr-Wilson, depending on the time, when am I going to use this in my everyday life? Like, it felt like we were never going to use these things, it seemed like. And that is a frustration of lots and lots of students. And so when it comes to science, I can easily say, well, this is where we're using it. This is what we're doing with it. And so one of the things that I want to make sure that we're comfortable with is some of these math tools to make sure that you are ready, able to use them and not worry about how to use them, to just use them. So we need to do a little practice to make sure that that's the case. So I'll do my best to present this. This is kind of a new game to kind of present and to have a video at the same time. We'll see how well it goes. So wish me luck. In physics, one of the things that we end up doing is we measure numbers that are either really big or we measure numbers that are really small. Let me see if I can turn this little bugger off down here. Stop presenting. Maybe it's this one. Sure, let's go with that. Thanks for your patience. And so one of the things that we're going to take a look at here is numbers like the diameter of our galaxy. Now, the Earth and the solar system that we live in are actually one small piece of this large kind of stellar organization that's called a galaxy. And then there's actually many, many, many galaxies that are spread throughout our whole universe that we're looking at. Our galaxy is called the Milky Way, and at the middle of it, there's more than likely a black hole that we're looking at. But we've been able to measure the diameter of our galaxy, and that is a whole different discussion as to how in the world would you measure something like that, considering the fact that we just stand here on the Earth and do that. And the short answer to it, without getting into it too involved, is that we can look up at the stars, and based on their color, we can actually know how large that particular star should be. And based on how bright those stars are, we can find out how far away that star is. So at a particular distance from it, it needs to be this particular brightness. So we can say, hey, look at that star. It's this color, and it's only this bright, so it must be this far away, which is important for us to recognize. So we have a way to gauge how far away stars are from us. So we can start to looking how far away is the galaxy, or how the diameter of our galaxy. On the super small end of things, we can actually determine things like electrons. Electrons are one small piece of an atom, right? It is the kind of smallest subatomic particle before you get down to finer structures like quarks or strings. And in our case here, the electron is almost no mass. I mean, it's so darn small. You can see that number that's right there, and that number is minuscule. That's a lot of zeros after the decimal point. But what I'm saying here is that in physics, we work with these huge numbers and we work with these little tiny numbers. And it's pretty easy for us to mess up if we were to use these numbers to calculate things. And so scientific notation is a way for us to go ahead and kind of compact the way we write these numbers so that we can do things accurately and do the math accurately to be able to support our understandings of the way the world works. So that's what it is. It's a tool for compacting numbers that are written in what we would call standard notation, would be very long to write down. And sometimes we abbreviate these numbers by approximating them, but it's important to realize that in order to write them down in a compact form, we need a tool like scientific notation. And so I'd like to start out with scientific notation. If you are a scientific notation genius, by all means, skip this entire video and just kind of move on. But if you want a little bit of a refresher on scientific notation, that's what this is all about. So let's get into it. Scientific notation has three parts to it when you write the number out. The first part is the number itself. The second one is this kind of times 10 to the, and then the last one is an exponent that fits up here. So again, the number times 10 to the, and then the exponent. The number sometimes has a decimal point in it written down, and sometimes does not. So that's important to recognize. The times 10 to the always looks exactly the same. It doesn't change. So this is a component part of it that doesn't change in any scientific notation. We use the x for times in this case, and then the exponent changes to either be a positive number or sometimes a negative. Now, if you were to take a number and you were to multiply it by 10 once, the only thing you're really doing to the number, if you're writing it out, is you're moving the decimal point to that number to the right one time. Think about it for a moment. If we take the number 1 and we multiply by 10, you get the number 10. 1 times 10 is 10. Okay, so that was easy. But really, it's just moving that decimal point that was after the 1 over to the right by once, and you get to the number 10. If you take the number 10 and you multiply by 10, you get to 100, which moves that decimal point just over the right one more. You just add another 0. If you take 100 and you multiply by 10, you get 1,000. If you take 1,000 and you multiply by 10, you get to 10,000, and so on. So as you're going, you're adding additional zeros every time you multiply by 10. And using these exponents right here is a way of saying, well, how many times am I going to multiply by 10? So this number here is 1 being multiplied by 10 2 times. And so if I take 1 and I multiply by 10 once, I get to 10. If I multiply by 10 again, I get 100. So 1 times 10 to the second is also 100. Now, 100 seems a lot easier to write than this. And you're right. We don't often write this in place of 100. We usually just write 100 down. But nonetheless, that's how it kind of works. If you end up with a negative exponent, though, negative exponents is a fancy way of saying we're going to divide by 10. So that's how we write divided by. And if you take the number 1 and you divide by 10, you get 1/10. And if you divide by 10 again, you get 1/100th. And if you divide by 10 again, you get 1/1000th, and then 1/10,000th. And slowly, that number on the bottom of the kind of fraction, if you want to think about it, or how many times you divided by 10, right? It just keeps on going. And so we're kind of moving that decimal point to the left, if you want to think about that. So we're dividing when we end up with negative exponents and multiplying when we end up with positive exponents. So let's do a little practice and make sure that we've got it. The rules of scientific notation, meaning that if you have a number written in scientific notation, then these are two things that must be true if a number is written in scientific notation. The first one is that when you put a decimal point in the number, the decimal point has to sit just to the right of the first non-zero digit. And I'm going to point that out quite a lot, but that's an important thing to either write down or internalize. What does that mean? The decimal point always goes just to the right of the first non-zero digit. And that's only if you're reading from the left, which we do in English and we do in number reading Arabic numbers that we use. The second rule is that when you're writing in scientific notation, we leave off extra zeros. We're trying to simplify this. We don't really want a cloud of zeros around us. So we don't want to write any zero that is to the right or to the left of the first or last non-zero digit. You can look at that again later and kind of internalize that. We're leaving off the zeros on either side of that first or last non-zero digit. So, okay, here we go. There are two other things that you want to remember here, and these two things to remember deal with the exponents. So let's go ahead and put those down. And that is, first, negative exponents divide by 10, and they typically move the decimal point to the left if you're thinking about saying, I'm going from scientific notation into standard notation. I'll show you that in a moment. And similarly, positive exponents multiply by 10, and you move the decimal point to the right, so you're making the number larger. So there's the two major pieces up at the top, and these are just kind of reminders along that process. So let's go ahead and see how this whole thing works with some very simple numbers. Let's start by going from numbers that are actually already written in scientific notation and then moving those into what we call standard notation. And that will help us to look at these rules and make sense of it. Now this number is already in scientific notation, and I know that to be the case because this decimal point is just to the right of the first non-zero digit, as read from the left. And I've got a times 10 to that, which means that I'm doing pretty well for scientific notation, and I've got an exponent. Now here's the thing. If I want to say, hey, I'm multiplying by 10 multiple times, I'm going to multiply this number, and it's got to become bigger. And to become bigger, I'm going to move this decimal point to the right. I'm going to do that 4 times. So here I go. I've moved it to go past the 8 once. And then once I get past the 8, I have to do it 1, 2, 3 more times to be able to say 1, 2, 3, 4. So now this number becomes 2,800, or excuse me, 28,000 is the number I'm trying to say. 28,000 as we go. So we move to the right 4 times and we get to 28,000. Now, similarly, if we were to take this number written in scientific notation with a negative exponent, we're asking, well, how many times do I divide by 10 instead, which moves our decimal point to the opposite direction, where I would move it to the left 4 times. So here we go. First, I would move it past the 2. That would be 1 move, and then 2, 3, and 4. Now my decimal point sits right here, and so when I write it down, my decimal point is here. I've got those 3 spaces, which I've now filled with zeros, and I've got the 28 that comes at the end. So 0.00028. All right, that's going from scientific notation into standard notation. But it's not as common for us to go from scientific notation to standard notation, to be honest. Usually we're trying to simplify numbers and compact them into a meaningful way that we can work with them more easily. So let's take a look at some numbers that are measured numbers that are ugly and should be written down in a way that simplifies them nicely. So here they are. And this just says try before you move on, and I'll give you a chance to do that in just a moment. So here we got the mass of the Earth in kilograms. Also a fascinating story how we measured that uses gravity. We'll get to there. The second one is the speed of light, so how fast light moves, which is ridiculously fast. And then the thickness of a human hair, super, super thin. And the diameter of a flu virus. Now, flu virus is a coronavirus, and so to be honest, this is about the same diameter as the COVID virus too, but also very, very small. So here's what I want you to do. If you know how to use scientific notation already, I want you to check yourself and watch this, pause the video, and see if you can go ahead and solve all 4 of these by putting them into what we would call scientific notation. If you are not savvy and you need a little bit of practice, hold on, and I'll go ahead and explain them. So pause the video, do the work, and we'll come right back. All right. If you've come back already, now this just says, did you get them? But underneath here, so did you? When you're looking at these 4 different ones, are these the answers you got if you tried them out? This is scientific notation for each one of these. Feel free to pause the video and take a look. If not, I'm going to go ahead and work through each of them, making sure that you understand how to get to these numbers along the way. All right, let's start with the mass of the Earth, making sure that we're all comfortable with how to take a number that's in standard notation and then to drop that and make it into scientific notation. First off, if we're going to scientific notation, that means the decimal point needs to live just to the right of the first non-zero digit, which is right down there. Second, I've written down all the other numbers that were not 0, which is what I've done right here. All the way up here, and then I've ignored all the other numbers to the right of that non-zero digit, so I've just left all these numbers off there. They're not important at this point. Now I dropped in the times 10 to the, right, so that's pretty easy. And now all I need to figure out is, well, how do I get my exponent? Well, what number should I write there? Should it be positive? Should it be negative? Well, important thing to recognize is if you are going to go from scientific notation to standard notation, this number gets a lot bigger. And 5.9 is a lot smaller than whatever the heck this number is, which is big, right? Thousands, millions, billions, trillions, quadrillions, and so on. I could probably figure it out, but I'll leave it there. So how do I get the 24? Well, I just count. I'm going to count in groups of 3. That's why the commas are there. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I've now moved the decimal point from here, which is where it lives on any extended or standard notation here, and I moved it all the way over to live between the 5 and the 9. So I needed to move the decimal point from here all the way to there, which is a total of 24 places, which gives us this number in standard notation. All right, let's see it again. Different number. Speed of light, not quite as big as the other one, but often written in scientific notation, so keeping that in mind. So I glance at this number right here, and I say, well, where does my decimal point live? Well, my decimal point lives right to the right, or just to the right of the first non-zero digits, which is the 3. So there's going to be a decimal point right here, but I didn't write the decimal point in there. Did I do this wrong? It's just not common. Notice it's all zeros after this, and I'm going to leave off all the zeros. So I don't really need the decimal point to sit there. If I tell you that I'm like 6 years old, I don't tell you I'm like 6 point years old, unless there's some fractional amount. And so I'm just going to write the number 3 and know that there's kind of a decimal point that lives right here. Now, the decimal point on this number lives all the way up here, right after the last 0. So in order to get the decimal point to live here, just to the right of the first non-zero digit, I need to move it all the way over here. I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to have it be a positive 8 because to go from scientific notation and put it back in the standard notation, I'm multiplying by 10 a lot of times to get the number to be bigger. So now I've got 3 times 10 to the positive 8, and that's the speed of light. All right, let's do it the opposite way around. Let's take a look at the small of the small. Thickness of a human hair, I want to go and represent this number in scientific notation to make it look like this. And so if I look at this number right there, I want to put a decimal point in. I want that decimal point to live just to the right of the first non-zero digits. So these are all zeros, so that's not the right of the non-zero. Here's the first non-zero digit. I need the decimal point to live to the right of that non-zero digit. So I'm going to move that decimal point so that it sits right there, in this particular case, between the 8 and the 4, and I'm writing that down, 8.4, right? I just took those two numbers, put the decimal point right in the middle. And then you'll notice here that when I went to scientific notation, I'm needing to move this decimal to the right to be able to get it there. In some ways, I am dividing by 10, taking this number 8.4, and I'm dividing by 10 5 times in order to get to this standard notation, or I'm moving the decimal point in this case to the right, to get to the scientific notation. Or down here, I would be moving the decimal point to the left to get to the standard notation. That's why those two things are kind of opposites of each other. So how many times? 1, 2, 3, 4, 5 is what I've got, and then I drop in that times 10 to the negative 5th. So I would divide by 10 5 times to get to this number, or I would move my decimal point over here. So negative 5th in the end. All right, and then the last one of these is the diameter of the flu virus. Same idea. You'll notice in this particular case, I did include the 0 afterwards because there's a 0 after the 5. And you might say, well, why not? We'll talk more about why that's the case when we get into kind of what is significant or what matters with measurement. Right at the moment, know that I've included that because that number actually is an important piece of our measurement. And again, you might not know why yet, but you will later in this class. So for now, know that I wrote 5.0. If I'd written 5 there at this stage in the game, there's nothing wrong with that. You're doing the conversion correctly. But at the moment, I'm going to leave the 0.0 in there because the 0 matters. And we'll get there later, not yet. So then I drop the times 10 in them, and then I'm going to put it as a negative, right? Because I need to divide by 10 multiple times to be able to get up to this number. How many times? I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, which is why I drop in the 8 there. So that's it. That's what scientific notation looks like, and many of you have it already. If you need some extra practice, I'm going to go ahead and give you an assignment today that's not super long. Those people that understand scientific notation, hopefully you'll be able to hammer those out pretty quick. And for those people that are remembering or have never studied scientific notation, take your time and try and understand it. There's lots of information online if you don't understand it by what I've explained. And so feel free to go and use those resources as you were. All right, the next video, we're going to talk about kind of units as a whole, and then we'll get into some conversions and we'll go from there. So math tools in physics. Yay. All right, bye everyone. I have to figure out how to turn this thing off. Well, let's try this again.